So let me start again. So today I will talk about this reduced length, which was introduced by Paramount. It's a very important tool, a new tool. So so this is very much like a generalization of this distance function to this Ricci flow setting. Okay, so in this these things can be today all the discussion actually work for any dimensions. So we consider say suppose I have a Ricci flow as usual. So okay, so say on the 0 capital T, okay, so sometimes it's a closed bracket here. So it's convenient to considering it's backward Ricci flow. So we start from some point, sometime. So we look at the backward flow. So then I have a flow of the flow becomes like this. Okay. So today I will use this parameter. Okay, it's more convenient this way. So now I can take any. Let's introduce the new length function here. So take let gamma be any this from say tau 1 to tau 2 first, okay, into your manifold. Okay. So giving any such a curve, and also say gamma tau 1 see is a point see at x, which I will fix this top. Okay. So then we define the reduced length L of gamma. So this one may also depend, for simplicity I will drop this, depends on these parameters. So this is so from tau 1 to tau 2 square root of R. Okay, so this is a scalar curvature plus d top. Okay, so this is a scalar curvature of g tau at evaluated at this gamma tau point. So here I will use the tau as a parameter. So on my metric we are parameterized by g tau here. Okay, so this should be more precisely. This should be a scalar curvature of g tau, then the evaluated at the point g tau. Just for simplicity, I just denote this by that. Okay, so have this functional. So maybe we examine this a bit. So for convenience, we will set x to be a gamma prime tau. Okay, so that's the x over there. So the first thing we so let's first take a look of this. Give an example to see. So let's say suppose M is just Euclidean space. Okay. So then what you do is we can take so the Ricci flow is trivial because then it's flat. So the g tau is just a standard metric g0, fixed metric because flow does not move because it's Ricci flat case. So then this term is gone. So also we can define a parameter like this. Okay, so let's rewrite this. I just use the same symbol for the curve parameterized by different parameter. See, this is a gamma. Maybe I put it this way. So tau. Okay. So then what we have is a gamma. This prime here is twice of s of gamma prime tau. is S. Okay, so maybe I change a little bit. So yeah. Okay. So anyway, so I get these things. Okay, yeah, that's right. I'm just looking at it in the wrong way. So then this gamma prime tau square is simply 4 of tau of gamma tilde prime s square. So this derivative is on s. So then you bring this in, and so this will become the L, this time the gamma tilde. Gamma is simply from S1 to S2 is half of gamma prime. Yes. So this is nothing else but the energy for curves. Okay, for curves. So this is extension of that. So what I'm doing today is basically I want to do what we did, just do what we did for this energy in the standard Riemannian geometry. Okay? And namely, I want to first compute the first variations, then compute the second variation, then I look at the corresponding length functions and compute the Laplacian, then give you a corollary, right? So to do that, maybe we first make some remarks. So here, because I take a square root of this, I first take this to be a bigger than 0. So you can compute the first thing, the first variation. Which I just so if you take a family of curves, say U of tau, defined to be a family of curves, say tau of U, and gamma tilde of tau 0 is just gamma tau. Okay, so let's take a variation of these curves. Then you can easily compute the U of at U equal to 0. So it's simply 2 of this. Maybe I write down this. Yes. So 2 tau of gamma y and x, and the tau 1, tau 2. Then the plus this tau 1 to tau 2, and this square root of this of y, and then this Euler-Lagrangian equation there. Okay. So this EL here means maybe I put so I save some space. So EL is these things I wrote here. Okay. So I say x is that's the tangent vector, the tangent vector of this curve, and star means the dual of this. So this is one form, and apply dual is become vector field. Okay. So this is rather straightforward. So the point here is I want to make a remark here is I always assume tau 1 is bigger than 0 to start with, because if you look at the Euler-Lagrangian equation, it has a singular has a tau in the denominator, so its equation looks like a singular equation. So at the tau equal to 0. So, but however, this is just because of wrong parameterization. If I change the parameterization into S, then that singularity will be gone. And so why we use this tau? Because this is a better parameterization for parabolic type equations. Okay. So first remark I want to say tau 1 is so maybe let's put this way. So in terms of S, so where y is simply infinitesimal variations, gamma tilde du u equal to 0. Okay, so in terms of S, so if so then if a say a s is just given by twice of s of x s square. Okay, so then the equation become like this. So dA a. So this is just a geodesic, and it appears in the equation of geodesics. So all other things is the correction from Ricci flow, and then plus 4s Ricci of a dot star 0. Okay, so then in terms of s, so that's a normal, that's a usual parameterization we do for geodesics. So then the singularity is gone, so you can make it s equal to 0. So this is true even for it's also true for so it makes sense when the s is 0. Okay, so this way we can make a remark here is that one can take tau 1 to be 0. So I will do that. I will always take tau 1 to be 0, and then the geodesic is so this time this exists, and maybe I put this way. Sorry. So as tau 1 goes to 0, this is square root of tau of a limit of x tau 1 exists. Okay. So from now on we will fix the. So now we fix the tau 1 to be 0. That will make a lot of computation simpler, and x is the fixed point there. Yeah, okay. So before I go on, let me say one thing is and before I go on, let me define air length. So this is also depends on tau bar, okay, and also depends on initial point x. So this is Q defined to be the infimum of all the air gamma, and gamma 0 to be x, and gamma tau bar to be Q. Take this. Okay, so I take it's an infimum of this. So this is very standard. Okay, so this is air length, and we know. So we also set up, because I want to state a theorem. So this air x and the tau bar, or maybe I put this way. So maybe tau bar here. Okay, so I put the air x of Q of tau bar to be so air Q tau bar over twice of square root. So this is definition. This is called the reduced length. Reduce the length. So the theorem we want to prove is the following. Okay. The theorem we want to prove is the following: is this if I look at the reduced volume, V tilde over tau, of course there's a base point x here, okay, which we fixed. And this defined to be a tau of exponential of air q of tau of dq. Okay. So dq here means the volume form of a metric g tau here. Okay. So this is a monotonic non-decreasing. So this is non-decreasing. So this is non-increasing. I'm sorry. So this is a non-increasing as tau goes up. So this is a key things. In the Euclidean space case, you can go back, try to check, and you can define these functions, and this will give you actual heat kernel of that. Okay. So what I'm going to do is I want to prove this, give you a proof of this. Okay. So basically, proof is there are two ways of doing this, like what we did in the Riemannian geometry. One way is we try to develop some so-called Laplacian comparisons. Okay, so this time we want to do a comparison for this computer certain Laplacian equation for this. Also, there's more like ODE type proof, namely, if I take this integrand and also take this Jacobian in the exponential map, in terms of exponential map, then I want to say integrand. Resulting integrand is non-decreasing, okay, pointwisely. So I will indicate how this is done. So the proof towards these both things, in a sense, are very similar. Okay. So let me go and how do I start? So first, let me make a definition. So now we start to prove this. So let's define so-called air exponential map. Okay. So let's denote this to be air exponential. Define on x. Okay. From tangent space, some open set, which in the, maybe I put D here, contain the Tm x, and also in the 0 to tau to infinity into your manifold. Okay. So it's defined by air exponential x of z of tau. Okay. Sometimes it's a tau bar, so just emphasize this will be fixed. Okay. When we study a corresponding geodesic, so this is just the z of a tau bar. If it's if this exists. Okay. So this is D is a defining domain. Stands for this is well defined. So where the gamma z from a 0 to a tau bar is the geodesic, is the air geodesic. With initial value gamma z 0 equal to x, and the limiting gamma prime. So this should be a tau limit. Sorry, I already wrote something not quite right here, but this should be inside here. Okay, so this is a tau, and tau goes to 0. Is z. So existence of this, at least for z and tau are small, obvious because we are just considering second order ordinary differential equations with giving initial point and the initial velocity, and we can always find a unique geodesic, so giving those initial conditions. So just get used to this strange notation condition there, because we use the parabolic parameter here again. Okay. In terms of S, that simply means derivative at 0. Okay. So we have these things. So and certain quite weak conditions on M, and certain appropriate condition on M, and this is air expansion map. As in the standard case of expansion maps, it's well defined on whole tangent space, and it's a smooth map. Okay, so this so air expansion is a smooth for on M for M with with appropriate assumptions. Okay. So on the other hand, what we are really interested in is not that expansion map. We are interested in this. So we can we just let's set plot things. Okay. So we plot this U, say U. Any questions? So let's plot UX tau bar. Okay, defined to be maybe I plot this way, tau bar. Defined to be all the Z inside the tangent space. So namely there's a unique, maybe I put tilde here. So there's a unique geodesic. So there's a unique air geodesic from 0 to this air expansion x of Z tau bar. Okay. So I should emphasize here is you might feel a little bit it's a bit different here is from a geodesic case, because geodesic case we define only on the tangent space, and there are certain homogeneity among the parameters, and this homogeneity is destroyed in this case. So that's why every time when I talk about air geodesics, I have to specify the parameter, ending parameter. Okay, here. So this air geodesic means from x. Okay. So UX of tau bar is just the image of this of x of UX tilde tau cross. Okay. So then we know understand clearly. So then we know. So air x is a Lipschitz function. So let me see. Then one can show the following. So air x tau. What notation I used? So air x is smooth on a UX. So air x tau bar is smooth on a tau bar. Okay. And in general, it's a Lipschitz function. Air x is Lipschitz, which I'm not going to prove. It's we did that in our book, and it's very tedious to do that, and it's not a difficulty. Okay. So in the following computations, I will concentrate on this part. Okay. Okay. So first thing, I make a few and record a few things. Maybe I use it here. So now, that's the first thing we can do is we compute this gradient of air. Okay. So first thing, I record first formula. So gradient of air x. Okay. So maybe sometime I will drop this x. So gradient it means in the gradient in the q directions is given by okay, and the 2 tau bar of x. So x is corresponding air geodesics. So all these formulas which I'm writing down here, I assume this is smooth, so I can compute the gradient and compute the Laplacian. So I always assume all those computations are in this region. Okay. So let's see why this is true. Because in order to compute the air length, okay, what we know is maybe I just show you the proof here. So where do I show you proof? Maybe so if I have a x and I have a q here, suppose this is one air geodesic. Okay, and since it's unique, so I have for nearby point here, I always have a unique geodesic. Okay, so giving any direction here, I have a family of unique geodesics. Okay. So now I take this family of unique geodesics as a variation here. Then I compute the derivative. Okay. So since this is a family of unique geodesics, so this time for this region, so air x of say this q prime here, the q prime and the tau bar is simply the air length of corresponding geodesics here. So let's see, this is corresponding, say, gamma u here. Okay, gamma u, the length of this. Okay, so then the computed gradient of this is like I just try to compute the variation of this air length. And now remember, I have a family of air geodesics, so this term is gone. So only thing this left here. And the tau 1 is 0. Here I take tau 1 to be 0. And also, since I fix the initial point, so the variation of the y, the infinitesimal variation vanishes at the initial point. So I only have one term. So that implies this. Okay, implies. So gradient is this. Okay. Of course, this is clear if I look at the distance functions, right? No. That's well known. So second, I want to compute. So this is so maybe I derive some corollary of this. So this implies the air x gradient square. So is equal to, okay, so it's equal to 4 times tau bar of x squared. Okay, so then I use so this I can rewrite this as a 4 minus tau bar of r scalar curvature plus this 4 tau bar. So this is just integrand in defining air length. Okay, so I just write this. So second thing I want to derive, if I compute d air x, d top and at the top bar. Okay, So what do you get? Of course, you get integrand. Okay, so you get integrand. So this is simply easy. Tau bar of r plus x squared. Okay. So and also there's a term because there's a term here because this q also varies in the. So so I have this I'm sorry. So when I do this, I mean take this derivative here. But on the other hand, if I take a full derivative in time, so I get this term. But I have to subtract the special contributions. Okay, that's why I need to subtract this here. So in the end, so this is just same as twice of square root of tau r and minus tau bar of r plus x squared. So of course here I already used this formula here. Okay. So now we can erase things here. So okay. So I want to write this both in a better way. So I should leave some space, but anyway. So next, what we derive, say let's compute this. R plus x squared along the algebraic. Okay. So this will give you following things. First is give you r tau. Okay. And then I also give a compute the norm of this. Compute the gradient r and x. Okay. So because these things both is a g tau and the gamma tau. Okay. So this is contribution only from here. That's a contribution from taking here. So then I take a derivative of this. Of course, the metric which I used to take a norm also depends on tau, so I get a Ricci curvature and use the equation. This is just give you twice of Ricci of x. So then I just pretend the metric to be a fixed. I will get twice of dx, x, and x. Okay. I'm pretending x is fixed. So let me just then I'm using an Euler-Lagrangian equation. You replace this by Euler-Lagrangian equation, and you do some manipulations. You will find that this is exactly like this. So let me just write down the result now. So this is h x and minus 1 over tau. Okay. So I say it again. You try to just use the equation, Euler-Lagrangian equation, to substitute this, and then you collect the corresponding terms. The capital H is defined here. So interestingly, this capital H, though I don't have time to expand today, actually it's not really needed in this course. This actually coincides with the trace hierarchy inequality of Hamilton. Okay. So this quantity appeared before in the hierarchy type inequalities. So once I have this, what you get is the following. So I get I can integrate this. So I get this. So now I look at the tau of 3 over 2 of this quantity here. Okay. So if I compute this, we will get things is this is and 3 over 2 of square root of tau of r plus x squared. Okay. Okay. And then I get this is a tau of 3 over 2 of h, and then this is minus square root of the same thing. So this cancels this. Okay, this cancels this. So if I integrate on both sides, I will get this r 3 over 2 of r of this is equal to k, some function k, depends on tau bar. Okay, which I did, and then minus 1 over tau. Sorry, 1 minus half of air Q. When I integrate both sides, this side I simply get length functions because just compute air length. Okay, of corresponding geodesics. So where this k, which I record here because it will appear later again. So this is just from 0 tau bar. It's not a local quantity. Okay. So let me rewrite this now. So this implies, so I bring this here. So this implies this is twice of a tau bar scalar curvature and minus plus. Okay. And similarly, you can also do it here. Maybe I need you to check. You can also express in terms of r, air, and k, okay. Which when I use it, I derived. Okay. So next thing I want to do in order to prove this theorem, I want to compute a hashing of this. So basically, I want to say third thing I want to do is I want to compute the Laplacian of this x. So I want to estimate this. Okay. So as usual, in order to do that, I want to just do a second variational formula for air length. Okay, so let me state the next result. So second variation. So fix the gamma from a 0 to tau bar is be an air geodesic. Okay, be air geodesic. And so let and the gamma u be a family of variations, be a variation. So variation, okay, such that it's a fixed. So then the y, then we get the following things. So the d square du square of air of gamma u So it's given by twice of top bar of y. So y is a time derivative is a derivative of this family of curves with respect to u, parameter u, and x at the top bar. Okay. And then the plus 0 top bar. Of so let me write down the things. So it's a Hessian of scalar curvature. Okay. So plus twice of and minus 4 times dy Ricci of xy. Today is a bit so many formulas. Probably this is a peak time for formulas. So then the plus twice of maybe I put here plus twice of. Okay. So if you forget about contribution from curvature, that's exactly I mean if you only count these two terms, that's exactly the second relation for energy. So those things come from a contribution from Ricci flow. So okay. So let me indicate the proof of this. Just quickly outline proof of this because it's rather straightforward, though it's a bit complicated in looking. So okay, so first thing we just make so first thing we know this d square of L gamma u of d u square. Okay, that's so this is nothing, just this term. Okay, because this is just acting on a okay, so this is just a y acting on a y x. Okay. So because this is a boundary term in the first variations, so then you have a term from 0 to bar and twice of tau of just the Jacobi equation. So here this is just a Jacobi equation. So Jacobi equation you can obtain by taking a family of these Euler-Lagrange equations and differentiate on the parameters. Okay. So suppose you have a family of curves satisfy this equation, then you differentiate this family of equation in the on the parameters, you will get this, okay, in the standard way. So in the second relation you should have this. Okay. So then you simply plug in this form of Jacobi equation. You do some manipulations. So maybe I and tell you what we did. Okay, in here. So if you just kind of reluctant to write down this. Let's see. What is the shortest time to do this? Okay. So now when we plug in this, so Jacobi is giving by Jacobi x y is giving over there. So now let's compute one thing. So we compute the next thing. Let's compute this. Okay. So we compute this term. Okay. Twice of tau of dx. So we want to integrate by parts. Okay. So basically, what we do is I want to change a second derivative here into this square of a first derivative. Okay. So then you get something more. So this will be directly. This is just tau of. So when you compute, first you compute this. This gives you dx y. Okay. I probably do a little bit faster. So then you keep this term. So you take derivative here, pretending a metric is invariant and time is fixed at time. So this gives you dx y, and plus twice of tau of dx y. Okay. So now your metric also changing. So what you get is okay. So maybe I just simply write down now. So then you get one term from here. So this is you get 4 times. So minus 4 times because there are Ricci curvature here. So this is minus 4 times square root of tau of plus of Ricci. Use Ricci dx y. Okay. Because the metric is changing with the time, with the tau, backward time tau. And then also the connection here depends on tau. So you have a contribution from this connection here. Okay. So let me just record it. So the computation is straightforward. I just don't do it now. So this, you will get something more of x. Okay. So this term comes from because connection also depends on time. Okay. So once you have this, I basically done. So it's so now you replace you replace this term, okay, by you look at here and the Jacobi equation. You replace this term by rest of other terms, and then you integrate by parts. So this term came out, and when you do integrating by parts, this will also you combine this. You get some new boundary term. You combine this new boundary term with this term here. What you will get is that will imply the air d u square. Okay, so if u equal to 0, so you get some boundary term like this. Okay, and cancel one of these here. So this you will get twice of tau bar of dy y of x tau bar. That's a boundary term. Okay. So then you also just replace the corresponding this term by rest of other terms here, and you just play around this, and you will find that this is exactly this thing over here. Okay. So maybe I want to write anymore. So this you will get 0 tau bar tau of things. I won't rewrite anymore. Okay. For example, certainly you get this term. You get this term here. Okay. And you get this term because from Jacobi equation, and you get Hessing from Jacobi equation. Okay. Because this is exactly Hessing. Okay. And this term dropped out because of this. Okay. So anyway, so you collect all the terms, you will find exactly this. So once we do this, we can compute the rest of we do next. We compute the Hessing. We estimate. Okay. Of course, we only do that on the smooth regions. Okay. So in order to do that, just as a Riemannian geometry, what we do is, in order to get good estimate, we have to pick up certain vector fields along the air geodesics, so-called adaptive vector fields. So let's, in order to do that, let's make a definition first. So let's say gamma is air geodesic. So y along an air geodesic gamma is called adapted. We didn't use this word in the Riemannian geometry, but actually we use the corresponding version in the comparison geometry. If this satisfies the following equation, x plus equal to minus Ricci of y dot star, okay, plus tau of y. Okay. So you can easily prove using this ODE. You prove the following: if y1, y2 adapted, then if you look at the pairing, you compute the pairing. Okay. So pairing is given by okay. And because metric depends on backward time, so there's some contribution from Ricci curvature here. That cancels this. So in particular, that implies the inner product of at tau is the same as tau bar over tau of inner product. Okay, so pairing only varies in the collinear way. So now what we do is we now want to use these adaptive fields as a variational fields, and plug that into these formulas to get the upper bound on a Hessing. Okay, So now let's suppose. Okay, suppose the variational field y is adapted. Okay. So then what we know, we know it's this air length of top this x of gamma u. Gamma u is the corresponding family of curves of at the top bar is always less equal to air length of gamma u. right? Gamma u. And moreover, at u equal to 0, x of u equal to 0, so gamma tau bar is exactly the same as gamma. So this corresponding to case u equal to 0. So then the maximum principle says the gradient will be the same. So I should say a derivative of d of Lx du restrict to gamma u tau bar is the same as and the second derivative. So second derivative is Lx du square is less equal to square. Okay, so I drop this just for simplicity. Okay. So that okay. So let's see where we are. So it's a so now we can compute the Hessing. So what is the Hessing here? The Hessing of Lx, okay, is by definition is a y. Okay, so this is Hessing in the y directions. Of course, we compute at u equal to 0. Okay, so this is equal to y and y Lx minus x. Of course, everything at the top bar. That's just, and this will be less equal to this this d square u square and the minus, and we know this is just twice of tau bar of dy x using the first formula on the left corner. Okay, so this exactly is a boundary contribution in the second rational formula. So what I get here is this is just equal to this from 0 to tau bar, okay, of square root of these things here, and things I wrote here. So boundary term cancel out. Okay. So okay, so what we it's pretty much done here. So it's and so we need to just write out the conclusion. Okay, so we have these things here. So one thing we need to do is we have a okay. So y. Okay. So I have to remember this is y here is simply this is at the point tau bar. So this is really y here is a y tau bar here. Okay. And y is a depth field. Okay. So now let me go to see what the yeah. So what will I do next? So let me just write this now. Okay. So I copy some of these terms here. So since in the bracket with dots there is the things here. But next I want to replace these by using this equation here. Okay? Because y is adaptive fields, I can replace this by these things. So what you do is I just copy down things. So I get this is from 0 to tau bar, okay, and the square root tau of a Hessian of R of y. Y is an adaptive field, okay, and plus twice of remaining curvature. Okay, and minus 4 times this dy Ricci of xy and plus 2 of Ricci of yy. 2 of Ricci. Okay, and integrate against the d tau. So there's other term which I keep this separately because okay. So this is given by y tau bar square. So I will tell you why this comes in. So square root of tau. Okay. And minus d tau. Okay. So of course this term is okay, and this term is there, and also this term is there, and this term is there. So what I did is I simply replace this by using an equation for adaptive vector field. Then you will get some because there are some term here. You will get a square of y, but then I also use the things here. So here I will use the fact. Use the equation for adaptive fields for y, and the fact y tau square equal to tau bar tau square. Okay. So that's why you see this. So originally this should be a y tau square. So the reason to that next you do integration by parts again. I write this. Okay. So to save time, I write this from 0 to tau bar. Okay. And square root of tau. Then h x y. That's again in a is that quantity are defined there. Okay. There's a quantity defined there. And it's quantity defined. So it's actually also appeared in the hierarchy in the called the Hessian type. So then you write this. Of course, this step is very trivial. I basically write this, then collect all the other terms in one thing. Okay. So maybe I'm not going to write out. So I collect all the things here. And these things will certainly involve this. And we are also involve some terms in the h, but not in the previous integram. For example, we are involve this term and this term. Maybe not involve this, but certainly we are involve this. Okay. So anyway, so these things in the dots now are simply those terms which you have by introducing h. Also something which from here which are not used the h. Okay, yes? No question? No? Okay. So this is anyway. This I don't need to write down. I mean anyone can write them out in a few minutes. Okay. So what's good things is these things in the dots can be write as a complete integrals. That's things we need. So this, you compute the ratio of this, y tau and y tau. Of course, this is a ratio of g tau. Okay. And it turns out this is just all these things here. Maybe I put one more dot to distinguish it, to differentiate this from the previous things. Okay. So now you can integrate this. So what you get here, so now I can erase this. I don't need this now. So in the end, so I get the formula which is rather clean. Of course, this integrand has many terms, which I just write in short. So sometimes like you do a classification. So if I have too many things put into a class, give a name, then done. So like classification of complex surfaces, they call the surface of general type. Actually, there are maybe 95% of them are there, which we don't know too much yet. At least there are a lot more to do. So yeah. So anyway, it's a joke. Okay. So now what we have now? Just got the. So in the end, so I can. So maybe I just write down the formula. Okay. So once I did all these things, so what I get is this is the Hessing. So and of Hessing of this air x q air x at the dot and the tau bar and the y tau bar. Okay. So it's bounded equal to a y tau bar square of a square root of tau bar and minus twice of. So this comes from that Ricci for derivatives. All these are good terms because they only depend on pointwise property of y. So next one is a global term. It depends on the adaptive fields along the path. So this is square root of tau. Okay. So one more case. So one more case is a thing to examine. Namely, it's very nice to know. So if equality holds, what happens if equality holds? So all these computations I did there are holds. Namely, equality holds if and only if y is a Jacobi field. Because at that time, if it's equality holds, at least this air is same as this family of these lengths of curves is same as the distance, okay, air distance. So it's a adaptive field and the Jacobi field. Okay. So y is adaptive field and the Jacobi field. Okay. So this allows us to conclude the things is as follows. So maybe I state a lemma, which I use later too. It's also standard in the sense because in the remaining geometry, for example, Chiga-Evans book, we certainly saw things like that in that setting, okay, corresponding in that setting. So this lemma is the following. So lemma says if this y is this is general lemma, not necessarily this here. So let's say if y is a Jacobi field, maybe to distinguish that is if and adapter is also adapt. Okay, so to remind you. But in this lemma, it's not necessary to be adapt, just Jacobi field. is a Jacobi field, so or air Jacobi field. Then along the air geodesic, gamma, then you have the following things. Then this Hessing of air x tau bar, okay, at y tau bar is simply twice of tau bar. Okay. So why is that? This is So why is that? So the proof actually is very easy, because if a variation is given by family Jacobi fields in the previous, I guess, erased in the previous second variational formula, there's no integral, because integral involve Jacobi equations. So only boundary terms. That's how you get this. Of course, you also use the fact that dxy is the same as dyx, because two fields are commute. So you have this. So now, if I apply to this here, that means if I apply to here, if y is also adapted, say, then and this term here, you can replace by Ricci. So this term here is simply a minus twice of a square root tau bar of Ricci of y, and then plus square root of tau bar of y. Okay. So let me rewrite this. So the equality holds if and only if the equality holds. So let's rewrite this. So this is here now. So equality holds if and only if. So this time it's a Jacobi field. Then this is or at least let me state this way: only if. It's actually if and only if. That's but to. So it's a Hessing of air x tau bar. Sorry, dot tau bar of y. Let's just drop, and then minus 2 of square root of tau bar equal to Ricci curvature of y minus so this is just like a Sauterton type equations. Okay. So this is like a Ricci Sauterton equation. I mean in y directions. So if this Hessing has if you have a equality for Hessing for every possible directions, then the condition is this corresponding equation metric has to satisfy Ricci Sauterton equations, because that's true for all the y. Okay, all the y. So that's okay, so let me wrap up now. So once this is held, so I can give a corollary. So give a corollary of this is a follow. So we get we compute the Laplacian, which is of course the trace of this Hessian x tau bar, okay, of at point Q. Sorry, at the point Q tau bar. So this is next equal to. So first you start summation of take a Hessian here. So you take a orthonormal basis here. So you sum up over this, you get n. Okay, n over square root of tau bar. So you take a summation over Ricci. Take a summation of Ricci over the orthonormal basis, you get a scalar curvature. Okay. Of course, scalar at that given time. So then, okay, because you take a trace of this, take a trace of this. The trace of this, you will get the H there. So here, just need to be careful. Of course, here, if I choose orthonormal basis, you have to make sure along the whole geodesic is still orthonormal basis. But that's fine, because the lemma I said before, this for adaptive fields, the pairing just vary according to scalars. Okay, so by scaling appropriately, you will get the scalar. You will get the orthonormal basis along whole path. The only loss you have is you have to add up some. You have to add some actual tau here. Actual tau here. That's why in this definition of k, which I guess I dropped, is and maybe I write here. K is tau bar is 0 to tau bar of tau of 3 over 2 of hx. So this actual tau exactly comes out from because in order to take a trace here, you have to choose orthonormal basis. You have to normalize this. So now we conclude here. So let me write here. So n over square root of tau bar minus 2 square root of tau bar of RQ and plus k plus minus, sorry. K could be complicated, but then it has the k here. It cancels out. Okay. So the corollary of this, again. Okay. So let me just simply write down now. So air, you combine all this, air x. I will write this equation here now. Tau minus air x. And plus well, and minus scalar curvature plus so this is easy, just do a direct computations. So, of course, this is only true. So far, we only proved this. So I make a remark. So far, I only proved this on the smooth domain of air x. Okay, so this is only so far only proved on the smooth domain of air x because we need to do a compute the Hessian in a standard sense, and it takes some efforts, but it's possible. Just like in the sense in the case of distant functions in Riemannian geometry, you can make this to be true on whole manifold in the sense of distributions. So I make a remark here. So this one here, the star So right now it's only this is only defined U X tau. So which is dense, you can prove it's a dense set, open set in the N. Okay. So star also holds on M in the sense of distributions. So this needs to be proved. You can look at on the book, the chapter 7, the first two sections of chapter 7 in the book. Okay, in our book. So let's first, since my time is up, so actually I'm supposed to leave a few minutes earlier, but anyway, so now let's see. I can prove. Suppose this is the case, we can immediately prove and this theorem I stated. So now I compute the reduced volume tau, okay, of X. So this is like this. Right? So now, once you compute the derivative, so this is a d of this is m of this tau n over 2 exponential minus Lx. So then the contribution from here is minus n over 2 of tau. Okay. Okay. And then there's a contribution here, which is minus d Lx d tau. Of course, volume form also depends on tau, so that will give you a scalar curvature. This is backward flow, so it gives you a scalar curvature dq. Okay. So this is bigger equal to or less equal to, because so less equal to this n tau of n minus 2 of Laplacian Lx minus or not. Minus, it doesn't matter, plus a gradient. But this is 0. You do integrating by parts, they cancel out. Okay. So that gives you a theorem. So if you don't want to go this way, there's other way to do that. Yeah, or let me just tell you. It's and using this lemma, and other way of doing that, the other proof is you look at define u x tilde to be of tau to be of z in so like pre-image of ux tau. Okay, so then this v tilde x tau is just you do a change of variables, just ux tilde tau, okay, and tau of m over 2 exponential of Lx composed of L inverse. Okay, so then the Jacobian of dz. So this is the Jacobian of L exponential. So if I pause this to be say define this to be L z tau. So then a proposition is the following. This already in all things already done in this using this lemma and the computational hashing. So this is the following: for each z, L z tau is decreasing. Okay. Here I make a remark. This makes sense because ux tau theta is contained ux tau prime if tau prime is less than. Okay. If you already have an L geodesic up to length tau, of course, for you take a short section of that, you still is a unique L geodesics. Okay. So you can, if you fix some tau bar, and you do, let's see. So L, maybe I put this way, tau bar on 0. Tau bar. Okay. So that's what I have. Maybe I put it this way. So then if you use this, you can also deduce the monotonicity. There. So the computation is same. I already computed this. Because I computed hashing of this. So I already computed this, okay, and on the smooth part. And then what you also need is just compute the derivative of this. Okay, derivative of this is just related to computing Jacobi fields, variation of Jacobi fields. This we are guaranteed by this. You can use this to relate to hashing of long-distance functions, and then you bring it back to cancel whatever comes from here. Contribution. So in the end, you will get this. I stop here.